Section 11.3, we're doing Taylor series. We've basically been working with them all along, they just haven't really given them a name. And it's Taylor series or it's Maclaurin series, depending on where it's centered. So if we talk about Taylor, that covers everybody. What you need to notice, it's easier to do this if you notice the pattern than it is to try to memorize the formula. But you're trying to find a polynomial that approximates another function, and you're going to start it centered at A. Now, if A happens to be 0, then it's a Maclaurin series. This is A equals 0. So you plug in A into the function. Then you take the derivative, plug in A, and then it's x minus A. The next one is the second derivative of A. It's x minus A squared all over 2 factorial. Then the third derivative of A, x minus A cubed over 3 factorial, and so on. Now, if you look at these terms, you'll notice, look at the third one, the third derivative. It's a third derivative. The power on the x minus A is 3. The factorial in the denominator is 3. So they're all the same. So if I back up the second derivative, x minus A squared, 2 factorial. So this first one, first derivative, it's x minus A to the 1, there's a 1, and over 1 factorial. So this guy, the very first term, would actually be f of A, x minus A to the 0 over 0 factorial, and 0 factorial is 1, and x minus A to the 0 is 1, and so that's why it's just f of A. So to write it as a summation, all you have to do is take the derivative, the term number you're on, plug in A, put it over k factorial, and then it's x minus A to whatever the k, the number you're on. If it's at 0, if it's centered at A equals 0, then it turns into the summation k equals 0 to infinity, the kth derivative at 0 over k factorial, and then it would just be x to the k. This one is known as the Maclaurin series. Up here, this guy is known as the Taylor series. So Taylor series encompasses all of them. Maclaurin is a special case. So let's look at example 1. They want us to find a Maclaurin series, so it means centered at 0. Part A is for f of x equals cosine of x, and we're centering it at x equals 0. So you take the function, you evaluate it at 0. The cosine of 0 is 1. You take the first derivative, negative sine of x, you evaluate it at 0, and you get 0. Take the second derivative, and we're going to keep going here. There'll be negative cosine of x, so I get negative 1, until we see the pattern. This would be sine of x at 0, gives me 0, and now when I get to the fourth derivative, it has rolled its way around. We're back to cosine. And so it's going to repeat itself after that. So now I have all of those derivatives. Now all I have to do is write the polynomial. So I start out with f of x, whatever it was, that's a 1. Right here is the starting point. So the polynomial is p sub n of x would be 1, then plus 0, x to the 1 over 1 factorial, minus 1, x to the 2 over 2 factorial, because that's this guy right here. Then I'm on the third derivative, so that's 0, x to the third over 3 factorial. The fourth derivative is 1, x to the fourth over 4 factorial. And then it's going to be it's going to be 0, then it's going to be negative. And so this summation alternates. But notice what's happening. You lose all the odd terms. The next one that would count would be negative x to the 6th over 6 factorial, plus dot, 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 which would turn into a summation. Now we got to figure out what's generating this. Start at 0, go to infinity. We need it to alternate, starting with a positive answer. So that will do that. We need the bottom to be even numbers. So 2n guarantees even, so 2k, excuse me, guarantees even, and x to the 2k. The reason I'm saying 2k is This is the 0 term, this is the first term, and the exponent is 2. This is the second term, and the exponent is 4. This is the third term, and the exponent is 6. It's always twice the term number. So I generated the Maclaurin series for it and written it out of a sequence. They asked me to do anything else with it. Give the interval of convergence. To get the interval of convergence, we would use the ratio test because we see factorials in there and powers of k. So it's the limit as k goes to infinity. I'm taking the summation piece, this guy down here, replacing all the k's with k plus 1s, and I'm putting absolute value on it. So I can leave out that alternating piece, the negative 1 to the k, because the absolute value is going to eliminate it anyway. So I'm going to leave that part out. So I have x to the 2 times k plus 1 over 2 times k plus 1 factorial, divided by the original, which I'm going to flip over and multiply. So I have that. Now, what you've got to pay attention to on this is that x to the 2 times k plus 1 is actually 2k plus 2. So when I cancel, the x to the 2k on the bottom cancels with the x to the 2k on top and leaves you with an x squared. This factorial is 2k plus 2 factorial, which if I start writing them out is 2k plus 2 times 2k plus 1 times 2k times 2k minus 1. So from 2k down, that would be factorial. Hopefully that makes sense to everybody. Because I'm writing 2k plus 2, drop it by 1, 2k plus 1, drop it by 1, 2k. The next term will be 2k minus 1, then 2k minus 2. But from that 2k all the way to the right would just be 2k factorial. So that's going to cancel with that. And so I am left with, on top, number-wise, I just have a 1. There's no numbers. Over, I have 2k plus 2 times 2k plus 1. And the stuff that needs to be in the bars is the absolute value of x squared. So as x goes to infinity, as k goes to infinity, this piece right here is heading towards 0. So this is 0. But 0 is always less than 1, and that's the requirement if you're using the ratio test. So it's always less than 1. That means this thing converges everywhere. So the radius is going to be infinity. The interval is going to be negative infinity to infinity.